Swayam Prabha. Digital India. Educated India.
So today will be our introductory class, in which I will tell you some basics about this subject, as well as you will see that this semester we are going to have a continuous evaluation. So maybe after each chapters or after completion of each topic, we will go for some assignments, and you have to submit that assignment, because we are not going to have any mid semester or end semester, but it will be a continuous evaluation, keeps on going. So you have to comply with the time deadline given for each assignment to be submitted, so that we will get updated with your improvements, as well as we will go for some sort of a quizzes also, and that will be informed during course of time. Okay. So already this class was started. 2 classes has already been done, and out of 4 credits I am going to take 2, and my timing will be Wednesday and Thursday slot. Friday slot will be taken by Professor Dev. Okay. So in today's class we will see, I will tell you about the reference book which you are going to follow. Then we will discuss about the syllabus, then some of the terminologies which we are using, and some of you might be knowing about all of them, some of them. So we are trying to keep everybody on the same platform, so that after that we can move forward. Okay. So you'll see this content of today's topic. Today's class will be this. Like terminologies, you can see engineering material versus natural material. Second, rock and soil. Then rock mechanics and geomechanics. Intact rock, rock mass. Continuous and discontinuous. Isotropy, anisotropy. Linear elasticity, nonlinear elasticity. Then strain hardening, rock discontinuities. Stresses, homogeneous, heterogeneous. Child, dyne, physical and mechanical properties, and rock classification. Okay. So the books which we are going to follow in this class will be, one book is written by myself and Professor Dev, Fundamentals and Applications of Rock Mechanics, which will cover all aspects of this rock mechanics, what we are going to cover it. But apart from that, if you are interested for other supplementary books for more study, so 4 of them I have written: Brady and Brown, Hook and Brown, then Hudson and Goodman. So I have already shared all these 4 books with you, and the book I have shared, the book written by me is not shared with you, because for that we do not have the soft copies. Okay. So these are the 5 books we are going to follow, and primarily the book which is written by us in due consideration of your topics is there. Okay. So the syllabus consists of these two parts. Left hand part will be taken by Professor Dev. Possibly he has already communicated with you. And right side part will be taken by me, which includes rock mass classification, in situ stresses and measurements, pillar design, artificial support, subsidence, slope stability. It will be, I will see even one more topic was there, in situ strength measurements, but I will see how much we are going to cover it, because this online mode we are going to be more interactive and have a continuous evaluation. So we'll try to cover most of the topic. Okay. So in your class, in this third semester classes, we are going to be very, very fundamental. We are not going into very deep into the principles of this rock mechanics. That's why we are calling it to elementary rock mechanics. So all the principles will be told to you, and we will try to see how whatever the principles we are using, right, stress strain relationships or the failure criteria, how those criteria can be used to design the real life structures like pillars or the support or maybe slope or maybe the subsidence. How these principles can be used for the design of such type of structures. So you might have known about the minerals, rocks and minerals in your school times itself. Like rock is made of one or more minerals, and minerals is a natural occurring substance having fixed chemical composition. So we are starting with this definition. We are continuing with whatever you have studied in your school time, and now we are extending into your engineering application of these rocks. You might be knowing that the formations of based on the formations, rocks are being categorized as igneous, metamorphic, or sedimentaries. So we are now going to use all these principles, how those rocks can be used for our engineering applications, so that our life will be more uh, comfortable. Okay. So starting with this mechanics, if you can define the mechanics, you all know is concerned with the motion of physical bodies and the forces that cause or limit their motions. Okay. And when we are talking about the rock, so it becomes a rock mechanics. When our material becomes rocks, it becomes a rock mechanics. So here we are talking about the physical bodies are your rock, and the forces will be maybe natural forces will be there, which we will talk about. We will talk about the rock, we will talk about the forces which are present in nature, and under which actions this rock is being, what type of behavior this rock is showing under different conditions. Like if I'm making a openings, underground openings, or if I'm making some slopes, so how this rock is behaving in those situations, and what are the forces which is going to act on such type of structures. So I had talked about one term, geomechanics, which is very, very common as far as the civil engineers are concerned. So geomechanics, when we will talk, it is a branch which talks about both rock and soil. So we are talking about only rock. So that's why. So geomechanics is study of engineering behavior of soil and rock. But if you'll see the civil engineering people, they will only talk about the soil, not rock. So, but their specializations are more or less calling geomechanics. Okay, so what are the scope of rock material? If I'm talking about the rock, what are the scopes? Okay, so you can see the next slide. You can see the next slide. So these are the three ways we can use this rock. Okay, one is like a foundation material, like it can act as a support for a multi-story building or high-rise building, or like in this figure you can see the bridge is being shown over here. So this rock is acting as a foundation material. Okay. Second figure on the right side, this is from Ellora Caves from Maharashtra. You can see we can make a structure out of rock itself. No? We can have a excavations, and we can have the openings within the. We can use this material as a structure itself. Okay. And also third utility of this rock is that you can construct the excavations within the rock itself. Like you can see the bottom one, a type of mining. This is a type of mine that is called the shaft mine, and we can see this is large. height of this excavation is almost 2.2 kilometer long and almost 700-meter wide. So this much area was excavated in the rock, and we want that this rock to be stable in such type of situation. Okay, so if I go back to the scope of rock material, we will see that we can use that rock as a building material. We can use it as a foundation material, and you can make this structure built within the rock material. Okay, and you can say some of the examples are also written. Not only the structures in the rock is confined within the civil utility, but for the military purposes also we are or for the mining purposes, civil utility, or for the military purposes also, lot of excavations have been created within this rock body. Okay. Now, the first term which is coming to our mind, we are defining two terms as we are calling this rock as a rock material. If I can consider this rock material, there are two type of rock we are defining. These are the one is called the intact rock, and second is called the rock mass. Okay. So if I am talking about this intact rock, you can see the smallest circle. Is it the smallest circle you can see? And as the size of the circle is increasing, this is smallest circle you can see. And as the size of the circle increasing, the number of discontinuity, the amount of discontinuity or the weak planes within that size of that circle is increasing. So a smaller circle, you will see that the no weak planes are there, no discontinuities are there. In geological term, we are calling it a discontinuity. So no discontinuities are there, but as the size is increasing, the number of discontinuities are increasing. Okay. So the smallest elements of the circle that we are calling, which is devoid of any discontinuities or void weak plane, we are calling it as a intact rock. Okay. When when the rock material consists of joints or the discontinuities, we are calling it a rock mass. Okay. So rock material without any discontinuities, we are calling it a intact rock, and rock with discontinuities we will call it a rock mass. Okay. Now you look at this slide. In this slide, you will see I am trying to show you one cylinder rock which has been taken out from that block for testing in the laboratory. We are creating a samples of a small size of cylindrical shape, and that is being tested in the laboratory. And if you can see this photograph, this rock sample doesn't contain any discontinuities or fractures or weak planes. Okay. So this is a example for a intact rock. So generally we are using this intact rock for testing purposes in the laboratory. Laboratory in the sense the laboratory in our on a small scale, where we can use all this material to find out their properties. Some of the properties may be the compressive strength, maybe tensile strength, shear strength, cohesion, friction angle. We'll come across with all these properties later on. And possibly you know all these property. Modulus of elasticity, Poisson's ratio is very common for you. So all these property we can determine in the laboratory itself. Okay. So for the rock, as you have seen solid mechanics, you have the modulus of elasticity, Poisson's ratio is very common. So here also we'll find out these property in the laboratory. Okay. So we have a well-equipped laboratory where we can test it. So we are preparing this. So this intact rock is being tested in the laboratory to find out all these properties. Okay. So like rock mass, you can see the rock mass. If I'm talking about a larger scale, so intact rock we are talking on a smaller scale. Rock mass we are talking at a larger scale. So when we are talking about the larger scale, you can see this rock consists of lot of discontinuities. A lot of joints are there, a lot of fractures, cracks, and geological discontinuities are there. All these geological discontinuities or weak plane are making the structure weak, and that's why the strength is getting decreased. Okay, so if I'm using the same size of sample with the as an intact rock and same size of sample as a rock mass with some discontinuities, you will find that the strength of intact rock will always be more than the rock mass. This is a common sense. We can simply say if some weak planes will be there, so the strength of rock mass will be less than the strength of the intact rock. Okay. So sometimes we are also using, sometimes we are testing this rock mass as well in the field, in the at the place of their origin, uh, because uh, because all the structures, as you see, as I told you that the properties obtained in the laboratory is less than the rock mass. Okay, the properties of the intact rock is always less than the properties of the rock mass. So it is very important for the design people to know how much decrease is happening because of a particular set of discontinuities. That relationship we should understand, and for that purpose people are trying to find out the relationships. And how to find these relationships? Either we can do the experiment in the laboratory itself with some sets of joints, and find out the relationship between the modulus of elasticity of rock mass with the modulus of elasticity of the intact rock. We can find it out, and those results will be useful for the design purposes, because all your actual design slopes or maybe openings or the tunnels being created within the rock mass only. So we should know what this rock mass is, what the rock mass property is, we should know. And because of that, we need to know what is the property of the rock mass as well. So there are various methods have been devised how to find it out. We will discuss in our some of the classes, and we'll come to that. Okay. So I was talking about a so always when we are developing any theory, we are talking about some of the uh, what is called the approximation or the ideal conditions we are talking about. So here in rock mechanics or the rock material also, we have fixed our ideal conditions. What will be called the ideal condition for a rock, okay, or rock material, and that we are defining this ideal condition will be one of the property will be homogeneity of the rock material. Means the composition of the material will be same throughout its volume. So that is the homogeneity we are talking about. Okay. And the other extreme will be heterogeneity when it is not. So you can see in this figure, I am trying to show you three of the rock pieces, in which one of them you will find out the granite. Bottom one is the granite. You can see the black and white color is there. So those minerals are making it, and the distribution is not very uniform at all. So that is making this rock to be heterogeneous. Okay. Whereas in the top two figures, we'll see more or less the uniformity of your composition is visible. Okay. So this is very important when we'll talk about the when we will discuss about, and when we will try to develop the principles of rock mechanics. Okay, homogeneity and heterogeneity is very important. Then we are talking about the isotropy and anisotropy. Isotropy is a term which we are using, that the material property is independent of the coordinates, independent of the directions. No? Like you can see, one figure is shown over here. in this figure, a long cylinder is there, and we are trying to take the samples at various directions. And if I'm going to test it and found that all these properties are same, it means that the material is isotropy. If it is different, then it is anisotropy, means all the properties in all the directions are different. Okay. And why it is going to be different? It can be different because of this homogeneity, heterogeneity. It can be maybe different because of the bedding plates or the joints or the fractures which is being present within the body. Okay. So we have this isotropy and anisotropy, which is very commonly used in our rock mechanics subject. Okay. We have already gone through. So this is transversely isotropic and orthotropic. We are not going into that one. But transversely isotropy, for a particular bedding plane, the material will be isotropy, and in another plane it will be different. Okay, so because of the bedding with the layers or the bedding planes, I think bedding plane is new to you. So these layers will be different. The layers behavior will be different in different directions. And orthotropic, it will be in 3 different directions. We have the material properties are different. Okay, in orthogonal direction. Now, if you there is one thing which is very common, which common rock discontinuity is, that is called the joint. When we are talking about the joint, we are defining the joint having some roughness, and you will find that the strength of this because of this roughness, the strength in different directions are going to be different. So you can see that the strength are not, if it is circular, it replicates that it is a isotropic strength, but it is varying in all the directions. So it is showing you the shear strength of the material is anisotropic. Okay. So anisotropy and isotropy is very important. So I was talking about the strength. There are 2 types of strength: in situ or rock mass strength, and the laboratory and intact rock strength. So as I told you that laboratory strength will be more than your rock mass strength or the in situ strength. The reason is because of the discontinuity, presence of the discontinuity within the body, that is making it weak. Okay. So we will see that. Then the questions you can ask: why you are then, if you are finally finding the rock mass strength, then why you are talking about the laboratory strength? Because the reason is there. 2-3 reasons are there. One reason maybe is the simplicity of the equipment you have. With this small set of equipment, we can test the intact rock material on a large number with a small time frame. We can test multiple sets of experiments, multiple sets of samples. Whereas in case of rock mass, we need to have a large setup of equipment for the strength determination, as well as the preparation cost, the labor cost will be too much in case of rock mass determination, strength determination. So that's why we are preferring these laboratory properties over the rock mass properties, and possibly few of the rock mass property determination. If your structure is of very strategic in nature and very important as far as the safety is concerned, then we have to go for the rock mass strength determination as well. But more or less we are trying to avoid it because of the labor cost, the time consumptions, and the cost. These 3 factors are making this intact rock property more advantageous to determine than the rock mass property. Okay. And there are methods are there. Methods have been devised over the period of time, over the years, because this subject is more or less 60 to 70 years old. And over the years, the many researchers have given some guideline how you can find out the rock mass strength out of the intact rock strength. If you are determining intact rock strength in the laboratory and you do some sort of a visual inspection of rock mass strength, rock mass, and generating few of the datas, then you can find out the rock mass strength as well up to certain extent. And there is a method. So that's why we have a one chapter on that, that is called the rock mass classification. Okay. So we'll come to that in some of the classes, where we will try to find out how we can estimate the rock mass strength out of the intact properties. Some basic property you have to determine, and out of that you can determine the rock mass property as well. Okay. But as I told you, if because this is just an estimation, this is the rock mass strength is just an estimation based on the rock mass classification. So if your project is, or your structure is very strategic in nature, and it is a lot of safety is involved, so in those situations we have to go for some few tests we have to do in situ as well. Okay. So we have a chapter, we have a chapters, or we have was there how to find out the strength of a rock mass. Okay. So that chapter is also there in our syllabus. So how to find out the rock mass strength. Okay. And because intact rock strength you are determining in the laboratory classes itself. So we are not covering in the theory classes. You have the laboratory for that. So that will come up. Okay. And if required, I will tell you about the laboratory itself, and I will show you some of the laboratory tests, maybe some videos which you are not able to do this time. Okay. So while taking the classes, I will try to show you how we are finding some of the properties by the laboratory test. Short videos I can share with you. Okay, so when so in previous slide I was talking about the strength. Okay, now I am talking about the stress. Okay, so why we are talking about the stress? The reason is that for any sort of a structure, finally we are going to design any structures, and when we are talking about the design, we need to find out the factor of safety, and we want to find out the factor of safety of those structures. So that's why we need to find out what are the stresses or what are the forces acting on the body, and that is very fundamental. That is very fundamental, that to determine or assess or estimate what are the forces actually acting on the body. So this is what we are trying to estimate, that what are the stresses are acting. Okay. So you can see in this slide, it has been mentioned there are three basic regions to understand stress. Okay, first reason is that pre-existing stress. Like if I am making excavations below the surface, so before excavation, what are the stresses present in the rock or the earth structures or any of the structures? What are the stresses are there which is pre-existing? Okay, that we have to understand. So now when we are making some excavations, those stresses are getting changed because when we are making some excavations, those stresses are getting changed, and we have to find out whether though there is a change in a stress, or maybe there may be no change in stresses, there may be increase or there can be a decrease. These things can be happen. Okay, so we have to find out what is happening. So because of that, we are categorizing this stress to be of two types. One is called the in situ stress, which is pre-existing state of stress, and another is called induced stress. Means after excavation, what are the changes in situ stresses are taking place. So that is called the induced stress. Okay, and this is what we are more interested in. If I am making some excavation, what are the change stress of state around the body? Okay, so like I was showing you the open cast mine, a big pit excavated 2.2 kilometer long and 700-meter wide. So when I'm creating that much size of a structure, what type of stresses was existing earlier before excavation, and what is the stress are present or developed after creating this excavation? So that will be very important for us to know. Okay. So So the third point is mentioned, stress is a tensor quantity, and it is not encountered in everybody's life. Why we are calling it a tensor quantity? Most of you might be knowing. Tensor quantity we are defining. So we have three type of quantities we are defining: a scalar, vector, and tensor. No? So tensor we are defining the material, the uh, uh, the quantity having the magnitude, direction, and the plane. Here we have to define the plane of on which the force is acting. Okay, so based on that, we are defining the stresses. How we are defining the stresses? Force per unit area, where area is very small. Okay, so we are defining the stresses, and the stress are defining stress is a tensor quantity, and to define a stresses we need to define the three things: magnitude, direction, and the plane on which it is acting. Okay, so these three things are very important because the stress is defined as force per unit area. So force is already there and area is there. So two things need to be defined. So force you have to define a stress, and area also you have to define, right? So these are the reasons why we are basic reasons to understand the stress. And it will be more clear if I'm going to show you some more slides over here. Like you see this figure. If I'm talking about surface of the earth, and if you are going below the surface, and if you have a very small cube, very small cube, very small, like a dot, very small cube, I'm considering having the faces are very parallel to each other like this. The zoom part is shown over here. So we can define three principal planes on this cube. One is called, one is perpendicular to the vertical direction, and two will be along this direction. So in these three principal planes, we can define the three stresses, in situ stresses. And the notations you can see, one is denoted by sigma V, another is denoted by sigma capital H, another is denoted by sigma small h. Okay. So what is this sigma V? Sigma V is nothing but your vertical stress. We are calling it a vertical stress. And sigma capital H, because I am using a notation capital H, so I am calling it a major horizontal stress. That is called, because it is acting in horizontal direction, so we are calling it a major horizontal. So these two planes are perpendicular to each other. We know that the principal planes are perpendicular to each other. So here also the three planes are being defined, which is perpendicular to each other. So sigma capital H, sigma small h, and sigma V. Okay, so we have a minor horizontal stress and major horizontal stresses. Minor horizontal stress sigma small h, major horizontal stress is sigma capital H, and vertical stress is sigma V. Okay, so these in situ stresses, how we can find these in situ stresses? We have a topic on this. We have a topic to determine the in situ stresses. There are methods have been defined, and the people have instrumented the surface of the earth to find out what type of stresses are there at a particular point of time, and they have got a very good trend of that, and people are trying to find out what are the reason of the stresses, formation of these stresses, and now what is the relationship between each of them. Okay, because this is very important for the stability of the structure. Like for any structure, if I'm making, or for this cube also, if I'm trying to define the factor of safety of this cube, we will be interested to find the strength, and we want to interested to find the stress. So if I have the ratio of a strength by a stress, that is going to call as a factor of safety. So the strength is important, whether the strength of this block or cube is able to withstand that much of a stress or not. If not, the failure will occur. If yes, then failure will not occur. Means if it is not failing, means the body is, or this cube is stable. So that's why this stress and strength is very important for any such type of design. And we should know what are the parameters are there which is affecting these stresses as well as the strength. Okay, Okay, so then it will be easy for a designer for us to find out which parameter we can control so that we can design the structure economically and maybe economically. Okay. So different type, as I told you, there are different types of stresses have been defined. One is, as I told you, that is in situ stress or the virgin stress or the natural stress, which is present in the which is present in the natural state itself without any excavation. Whatever the stress is there, that is called your in situ stress. Okay. So these in situ stresses, there are varieties of in situ stresses have been defined. One is called the gravitational stresses, which is very common. Then we have the tectonic stresses, then residual stresses and terrestrial stresses. Okay, so these are the four stresses are there, which is categorized as the in situ stress. We will come to that, okay, later on. And next is your induced stress. When I'm making, as I told you, when I'm making any man-made excavations, maybe a mining or excavations, drilling, pumping, injection, energy, extraction, applied load, swelling, any sort of excavations, if you are making on you are doing in the rock mass, it is going to add or reduce. May it will add or maybe reduce the stresses around at that particular point. So that will be called the induced stress. Okay, so we will come to that. Okay, we will have a detailed study on this. So for say for example here, uh, like how to find out these stresses. Okay, so some of the one very small relationship have been defined based on the theory of elasticity, that if I know the vertical stresses, we can find out the horizontal stress. Okay, so if you know the Poisson's ratio, we can find out the horizontal stresses by this relationship. Okay. So that sigma small h is equal to nu by 1 minus nu. Nu is your Poisson's ratio multiplied by your sigma v. Nu, I think everybody knows what is nu, Poisson's ratio. Nu is defined as the lateral strain by longitudinal strain. What is lateral strain? The lateral strain is this direction and longitudinal strain is this direction. Okay. So a strain in this direction divided by the strain in longitudinal direction is your Poisson's ratio. Poisson's ratio. So we can find out the horizontal stress to be nu by 1 minus nu into sigma v. Okay. But this was the theory which was given long back by one scientist. But later on, it was find that this theoretical solutions is not valid in reality, because in reality, the horizontal stresses are, uh, as far as the surface is concerned, is much more than your vertical stresses most of the time. So the reason what we are estimating the horizontal stress using this formula is not valid as far as the practical application is concerned. So like you can see in this figure, in this equations, sigma h is always, sigma small h or sigma capital is always less than your vertical stresses. So this is not always possible. So for that, we need to find out the vertical stress. So before that, I can show you what is the, okay, I will come to that later on. Now the people have tried to measure this horizontal stresses and the vertical stresses around the world, and a lot of data. You can see the data points, and that has been plotted with respect to y-axis is your depth and x-axis is your vertical stress. So as your depth is increasing, we have these data points have been created around the world. Okay, and based on that, we can have a best fit line, which is something sigma v is equal to this is some constant k into z. This is nothing but your gamma z. Okay, unit weight of the rock. Okay, so we have this. This is a very linear trend. As we are going deeper and deeper, the vertical stress trend is sigma v is equal to h, density, gravity, and the depth. So this trend is more or less uniform all over the world. Okay, so that is the trend we have. When we are talking about the horizontal stresses, the horizontal stress, you can see the plot is given over here. The depth is y-axis and x-axis is your k, which is the ratio of sigma small h by sigma v. Okay, and you can see that this ratio When it is very close to the surface, 0 is what? 0 is denoting the surface of the earth, right? So right at the surface, maybe 250 kilometer, 250 meter below the surface, see, this ratio is more or less more than 1. Okay, the horizontal stresses are, the K is more than 1. Okay, and as we are going deeper and deeper, this is closing more towards 1. Okay, or sometimes less also. Okay? So this is the trend. There is no such trends are available as we are seeing in the vertical stress directions for the vertical stresses. But there are some, there is no trend at all when we are talking about the horizontal stresses. Okay, so to find it out, you can see some of the data are being clubbed and some minimum and maximum boundary has been defined based on these data points, right? So, so you will see that on the surface of the on the surface close to the Earth, we will find that the vertical stresses are, the horizontal stresses are more or less. You can see it has gone up to 3 also. Sometimes it has been reported 5 also, which is horizontal stresses are 5 times the vertical stresses. So we have to find out. So, so how to find out this horizontal stress? At a particular project site, we have to go for some instrumentation for their measurement. Okay? And we'll see that we have on chapter in situ stress measurement, that we will see how we can measure all these horizontal stresses. Okay, that I will see. So some of the details about what are the reason for this development of horizontal stresses. So I'm talking about some plates. I'm not going into that. Uh, uh, this is just for your interest, so that you can go into that. A lot of material is already available. Plate tectonics is the reason why the horizontal stresses are uh, uh, horizontal stresses are being developed, and why the horizontal stresses are more than the vertical stresses. That is coming from the movement of the plates, and this plate movement is being governed by the convections current which has been developed because of the molten magma. So you please go through that, and it will be very interesting if you have not studied all these plate tectonics. So it will be very interesting to find out why the high horizontal stress. The recently it is very interesting that the people have identified the problems in lot of engineering problems where the reason of failure of the structure or structure was the horizontal stresses only. And with the change of the direction of this horizontal stress, with the change of the orientation of your excavation, it's just solving the problem. We'll come to that. One more topic is there, that is called stresses around underground opening, and how we can control the stresses on any structure or any underground excavations to decrease their, to increase their factor of safety without adding any support or any sort of investment into for such type of so only the reorientation of the direction of your openings is going to solve your problem. So I think okay, before that this problem is very interesting, and you can see this problem is talking about a surface is there and earth surface is there, and below the surface at 100-meter depth we have to find out the vertical stresses and the horizontal stress. So as I discussed you, vertical stress is nothing but your gamma h. So this is discussed in the questions that find vertical and horizontal stresses at a depth of 100 meter from surface if the Poisson's ratio is 0.20 and 0.25, and I'm talking about not a isotropic property. So you can see that the material is anisotropy, so that in these two directions we have two different Poisson's ratios are there. So in two horizontal directions, x x prime, x prime, and y prime. Okay. If the average density of overlying rock is this much, or unit weight is 25 kN per meter cube, and average Young's modulus is 5 gigapascal, comment on isotropy and anisotropy. Okay. So as I told you, we can follow sigma v is equal to this, and sigma small h will depends upon this one, and we can have the sigma small h is 0.63 megapascal, sigma capital H is 0.83 megapascal. So you can see that it is not isotropy, it is anisotropic conditions where we have. Okay. Then in this case we are assuming that there is no tectonic strain, but when there is a tectonic strain of 0.1%, we can use this relationships to find out the horizontal stress. Okay. So one of the sigma h we will use 1.20, and for sigma capital H we will use 0.25, and this is your strain 0.1 percent strain, 0.1 divided by 100, we will use it to get these values. Okay. So in case of tectonic strain, you can use this relationship to find out what is the values in this case of strain. Okay. Okay. So so I will come to the blackboard. If you have any questions, I'm going switching over to the blackboard, sharing. Okay, please ask your questions.
So, the Poisson's ratio for this major horizontal axis and for minor horizontal axis are different. Does that mean that the material is anisotropic?
Yeah, it is different, so it is anisotropic.
Anisotropic. Okay. Okay. So it means like if it's the same, so it's isotropic, right?
Uh, please be slow.
Oh, so
Yes,
means if it's the same value of Poisson ratio, does that mean that it's isotropic?
yes. I,
And won't it depend on the vertical stress
so it is
acting on?
isotropy. So isotropy and anisotropy we are defining based on the different properties we have. So for the Poisson's ratio, we can say, okay, it is isotropy. For maybe other properties, it may be different. So as far as the Poisson's ratio is concerned, if both the sides, both the direction it is same, it means that it is isotropic.
Okay. Okay. Thank you, sir.
Any more questions?
Sir, hello.
Can
Sir,
you can you give your names also? Hello.
hello.
Yeah, please, please.
So why there are two values of sigma small h in the last question?
Sigma small.
Sigma small h.
Can you repeat your? Can you repeat?
So there are two questions in the last numerical. There are two values of sigma h in the last question. Why is that?
Sigma small h, and there
So
is sigma capital H. Yeah.
there are two values of sigma h small h only. One is 100 MP and one is 0.25 MP and one is 0.63 MP. Why is that?
0.25. So if you are using 0.25, you will get sigma capital H. If you are using 0.2, you will get sigma small h.
Okay.
So either values. Okay. So because if it is isotropic condition in both the directions, it will be same. If it is anisotropic, so based on the values of Poisson's ratio, we will get two different values of horizontal stresses. Am I clear?
Yes, sir.
Okay. Next. Next, anybody? Anybody? Okay, so any more questions? Any more questions? No. So I will add few more points here. Like if I if this is your surface of your earth, okay, and if I'm looking at any point below the surface, we are trying to define these horizontal stresses, right? So, so at this point we have this. Okay, as I showed in the photographs. Huh? So this is called your in situ stress. In situ stress. Okay. Now we are trying to find out if I am making my aim is what? If no excavations are there, so what is the in situ stress? If excavations are there, excavations can be of two types, right? One excavations will be something like this. You are digging something on top of the surface. So this material is being sifted and it is being piled over here. Okay. So we have the surface excavation. Are there? Have you seen such type of excavations? Okay. Now there are some other things maybe there. I can make some tunnels, metro tunnels for vehicular transportations. We can make, and maybe we can make some sort of a underground excavations, maybe a structure maybe of a square cross section or rectangular cross section or a large classrooms we can make below the surface. So what is happening to the stress field? We are talking about, we can also talk about the term called a stress field. As you are talking about the magnetic field, electromagnetic fields, here also we can talk about the stress field. And we can represent this stress field by, we can represent all this stress field by a line representing it. Okay. We can represent it by a straight line which is representing, this may be representing the vertical stress, and maybe we have a horizontal line. These horizontal lines will be straight when it is in situ condition. When in situ conditions will be there, the horizontal lines will be. Now, as you have seen in magnetic fields, if you are putting some sort of any resist something hindrance, so the fields are getting changed, right? So here also, if I am making any sort of openings, maybe of tunnel, very common for all of you. If I am making any opening over here, I am just removing this. I have planned for a large set of opening which has been created. I can make it more denser. If I can make it more denser. Okay, now I am planning to have a large underground tunnel of this size. Okay. What will happen to this stress field? What is happening to this stress field? The stress field is going to change their path. So I can delete all these things from here. So this part is being excavated by for development of a tunnel. So once this tunnel are being developed, what will happening to this stress field? The stress field is going to change their path and it will follow this boundary and again rejoin with the other end. It will still continuing. Similarly, this stress field is also changing its path and again match with the field which is there on the other end. Similarly, we can have something like this. This line will also bend itself and it will come here. This is also bent like this. Okay. So now you can see that the number of lines per unit area. What is the density at this location? That was a uniform density at this location, maybe at this horizon. But if you are looking at this point or this point or this point, the density of these lines are increasing. Okay. So the density of these lines are being increased at the different parts of around the excavations. So if this is happening, what will happen? The in situ stress which was there at this point, which was equal to maybe this value, sigma v was your gamma h, that value has changed because additional stresses have been added to this point because of the stress shifting from nearby areas. Okay. So this is happening to the any sort of an underground opening. One more example I will show you. Say for example, this is one set of excavations. I can make another set of excavations. Similar type of tunnel. We are making side by side. Okay. And we have surface. The stress field is like this. So what will happen to this area? Again, this stress field is going to be bounced back and again it is following something like this. Okay. So it will not go just inside it. It can just bend it somewhere and it is again going like. Okay. So you will find that again this area, when two tunnels are side by side, the stresses around that opening is going to be affected. Okay. So the stress field, what we are talking about, this stress field is getting earlier it is going to be increased, but now once second tunnel is coming side by side, this area is getting devoid of stresses. Okay, this lines is now no longer exist. Okay, this line will no longer exist. What you will find that for when one set of excavation was there was an increase in stress at this point, induced stress was increasing. But when we have a second set of excavations, so this point your stress has reduced to its in situ value also. So either thing can be possible. So that's why this induced stress is very important to find out. Induced stress. So in situ stress and the induced stress. So we'll find it out. Wow, how to find out? So when we are talking about the design, we have to think about if this stress reduction is taking place, whether that reduction is able to withstand by the material or not. And for that we have to find out the strength of this material and we have to find out the stress which is there. So for this purpose we need to have some sort of a measurement of this in situ stress as well as the induced stress when I am planning for the excavations, right? Sometimes there is no need. Nowadays we have the numerical tools are there through which we can estimate before going for such type of excavations. We can develop the numerically we can develop such type of structures and we can find out what should be the probable direction of stresses, what are the probable magnitude of stresses around the excavation. Okay. So anything over here? Anything at this point of time? Any questions? So this is what we have the underground excavations. Similarly, as I was, so I can have one more example is there. The stress is freeze. As I told you, the surface excavations. If I'm making some surface excavations and the material is being dumped and piled at nearby areas, what will happen to the stress at this point? Before excavation, maybe you have something sigma v was there and some sigma small h capital H is there. But once this excavation is taking place or some stress is being added, so this is going to be something changed. Okay, some increase or decrease will occur to these horizontal stresses. Okay, some increase or decrease will occur to these vertical stresses. Similarly, if I am making excavation here, what will happen to the vertical stress? This is also going to sigma v, maybe sigma delta sigma. Horizontal stress, if I'm telling it to be a tectonic, this is also going to have some changes. Okay. So whatever the excavations you are doing, if we are trying to do these excavations in the rock, so it is going to change the stresses in and around. And for the stability of this point, if your this point your value is such that if I am trying to find out whether this is failing under compression, no? Whether it is failing under compression or not, we have to find out the factor of safety. And we can find out the factor of safety by the the strength in compression and stress acting at this point. If it is greater than 0, greater than 1, it is safe. If it is less than 1, it is unsafe. And if it is 0, it is your limiting condition. So will not so your limiting condition. Okay. So we are talking. So
The
this.
video not so clear.
Hello.
The video so not clear.
और थोड़ा फोकस करें. ये photograph is not blackboard is not clear.
Yes, sir. Board is not clear.
Oh.
Sir, can't see a single word written on the board.
Single. Tell me again.
Sir, single word is not clear on the board.
Oh, okay. Okay. तो कैसे होगा? Okay, photographs are clear. Photographs are clear. Figures are clear.
No, sir.
Figure is also not clear.
Yes, sir. Everything is unclear.
और टीम में प्रॉब्लम है.
The figure is something clear, but written what is nothing show anything.
Okay, I can for today's class I can discuss. Maybe for next class I will do something else. Okay. 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 So for today we will discuss, and I can have the photographs, bigger photographs, and just I will discuss with you, so that from next class I will do something so that you will not face problem. So I was talking about this case. I was talking about the excavation, something like this. I was talking about Okay, you can see I am talking about a opening which has been created on the surface. Okay, and now when we are dumping it some other place or stacking at some other place, this is going to result into the change of stress in and around. In around the opening itself, the change of stress will take place. Okay, so if you'll see this figure, as I told you, the stress field, na? I was talking about the stress field. So here also you can draw in your notebook that how the stress field will change if I have open surface excavations like this. Can you draw it? And you can share it with me. That if I am making a surface excavation and if there is some maybe only surface excavation is there, how it is going to affect the stress field, because stress field was in before excavation it was horizontal, and now due to this surface excavation how this stress field are going to change. This is what we have to plot. I had plotted for the underground excavations. Now for the surface excavation, how your stress field is going to change, and you have to identify at what point the stress density, yeah, the number of lines passing through per unit area is more. If it is more, means that point is more vulnerable for failure. Okay, wherever it is less, means the stress has come down. If it is more than your in situ stress, like that. You can use your graph paper, no? You can use your graph paper and you can have this sort of drawing, or maybe you can use some softwares to get this plot, or maybe hand drawing also is good enough. So you can see that whenever we are making such type of opening, we are playing with the stress field. Once the stress field is getting affected, the change of stress is taking place at various parts of this structure. Somewhere it will be more, somewhere it will be less. Okay, and somewhere there will be no change. So we can find it out the area which is being influenced by this excavation. We can find it out what is the area or what is the zone around the excavations which is being affected by such type of excavations. So that area is very important. What is the area, or we are calling it a zone of influence? What is the area around the opening is getting affected by such excavations, and that area we are calling it as the area in which the stress field has changed. So that area we are calling it a zone of influence, the area in which the stress field has changed. And you will find that as we are going away from these excavations, maybe four times, 5 times the size of these excavations, we will find that the stress field is now no change is there. Now stress field becomes equals to your in situ value. So the area around these excavations are getting affected by such excavation activities, and as the size of your excavations will be more and more, the size of your zone of excavations will be more. Okay, so so if you are going to have a second type of or second structures you are going to make, so that is going to affect the stress. It will be not be created within that stress field. It will not be created within the in situ stress field, but it will be created in the induced stress field. So we have to be very, very cautious when such type of excavations are taking place already there, and we are trying to have another excavations side by side. So we have to determine what is the safe distance. What is the safe distance between the two excavations, so that it is not, the second excavations should not be affected by the first excavation. And that's why the knowledge of stresses is very important, And we will start with a topic for the stresses itself, because I think this will be a topic you will be more interested to know more about this. From the how to determine the stresses, okay, what are the methods are there, how by which we can determine these stresses, okay. And I will share you the slides beforehand. Maybe today itself I will share you the slide what I am going to cover up in the next classes, okay, so that you can come prepared with your questions as well, and so that we can clear the doubts in the class with the interactive classes itself, okay. So now this is very, very important to find out. So you can understand that the measurement of these two things are important: strength and your stresses, okay. Strength and stresses are important as far as the stability of any structure is concerned, okay, because our safety is being defined by these two parameters. Later on we will come to know that what will be the shape or the dimension is also going to affect the being affected by, is affecting the stresses, also affecting the strength. How these dimensions are getting controlling the strength and stresses, that we also will see when we will talk about the application of these principles for any design objectives. Design objectives for your any different types of rock structures, okay. Any questions here? Any questions? So any questions are there, please tell me. Any more questions? Oh, it is off or what? Any more questions? Okay, so there are three methods. Are there, which is talking about. I have these slides. I will share that slide. I can give you some. So you can see we have one agency is one scientific body is there, that is called the ISRM. Okay, this ISRM stands for International Society of Rock Mechanics, and we will see, and you can visit their websites as well. Okay, you can see their website isrm.net, I think. So you just have a search of ISRM, and they have a lot of materials are there as far as this development of rock mechanics is concerned, okay. So International Society of Rock, there are different methods have been developed over the years, but you will see only three, not three, these 5 methods have been considered to have considered to be been accepted all over the world for to determine the in situ stresses, okay. First method is your flat jack technique. Second is your stress relieving methods or overcoring techniques, and third is your hydraulic fracturing technique, okay. So we will see the first method, that is called flat jack technique. There is some limitations of this flat jack techniques are there. We will see what are the limitations are there and how we can make and how this method is being used to find out the stresses below the surface, okay. So if you look at this slide, some of the instruments, the different components of this instrument is shown over here. You can see this is a flat jack which has been shown, and I think this video is there. Or page not found. Okay. Okay, so this is something called a very flexible type of inflatable material. When we are putting the pressure through these hoses, it can expand, okay, something like that. And we have the hydraulic jacks. We can apply this manual hydraulic jacks or maybe automatic hydraulic jacks to apply the pressure into this. So there can be a variety of, here you can see this rectangular shape is there and this is your D shape is there. So it depends upon the type of our applications. The size of this flat jack will also vary. So in this plot, in this photograph, you will see that a slot has been created, excavations, a small opening has been created in the rock itself of rectangular cross section. The size is 2C and some depth will be there. Okay, it is a three-dimensional excavations have been done within the maybe wall of the rock, and we are inserting this flat jack into that. Okay. Once this is being inserted inside that, and you can see the sectional view, it is being inserted inside it, and we are inserting two pins, one pin on top, another pin on the bottom. We are putting two pins, one above the another, and we know the distance between them before doing these excavations. Okay, before doing this opening, we are putting two pins, and once we are placing this flat jack, what will happen once we are creating these excavations, what will happen, these two, the distance between two pins are going to decrease, because these excavations are created under the stresses, maybe sigma, some stresses, in situ stresses are there. Under the effect of that, we are creating these excavations. So once we are creating these excavations, the distance between these two pins are is going to reduce, because the force is acting from both the sides, and it is contracting. It is contracting the distance between the two pins. Okay. So this can be shown in this photograph that D naught is the point, D naught is the distance between the pin separation when there is no excavations. Okay. And once I am leaving it for some time, this distance is going to reduce, and after that some static conditions will come. When there is no, when after that the separation between two pins will be stable. Okay. Once this is stable after some times, and the jack is been fixed into that, we are now applying the flat jack pressure. We are trying to apply the flat jack pressure in such a way that with a very small rate, such that the separation between the pins again resume the same conditions, D naught. Okay. So you see, under the action of some stresses, the distance between these two pins has reduced, but again we are applying some stress to counterbalance it, so that again the distance between the two pins will resume the same, attain the same value D naught. Okay. So this pressure which is being measured by this hydraulic jack is called as the cancellation pressure. You can see cancellation pressure. The cancellation pressure we can measure, PC. So this PC is nothing but it is, so this PC should be equivalent. Theoretically, this should be equivalent to the pressure of in situ stress. Okay. So this is the basic principle about this method, in which we are allowing excavation to deform, and once it has been completely deformed, then we are applying the pressure to again regain the same sort of separation between the pin, and the pressure by which we are cancelling that effects of in situ stress, that cancellation pressure is nothing but it is equal to your in situ stress value. Okay. So what we are happening, we are cancelling this P naught by applying some pressure into the flat jack by this hydraulic jack. So this counter pressure is now equal to P naught, so that once it is countering it, so that then the distance between the two pins will be same. Okay, once it is same, so we are assuming that the cancellation pressure is nothing but your P naught. So what you can see that in this case, in this flat jack techniques, we are always measuring the stresses which is perpendicular to the plane, perpendicular to the plane of the slot, plane of the slot. So if I am making if we have a flat jack is there inside the slot, so we are making a pressure on top of it. The direction of your stress will be perpendicular to the flat jack surface. So this way we can also determine the direction of the stresses, as well as the plane is defined and the magnitude. All the three parameters are defined by this flat jack technique. Okay, so magnitude, we are getting into the this dial. Plane is already, we have created a slot, so that plane is already defined, and the direction will be perpendicular to this plane. So all the three parameters are defined, and if you know these three parameters, we can find out the direction of your stresses. Okay. Now you can see these photographs. In this photo, I am trying to show you that a flat jack has been installed between these, the slot is from this point to this point, and there are pins are being installed between at different points. Okay, and you can see that the deformation of these pins along this length will be different. If it is very close to the end, it will be less, and if it will be at the middle of the excavation, it will be maximum. Okay, so we are trying to have, if you want to have a very minute measurement of this excavations, because we cannot rely on the results of only one measurement, so we are putting 2-3 such type of pins or the instruments. There are different types of instruments are there for the measurement of these deformations at a very finer level. Maybe we cannot use a scale. The least count for a scale may be in centimeters, or maybe in millimeters. We want something called, which can measure the deformation in called something called millimeter scale, or maybe micrometer scales. Okay, so for that maybe we can use the dial gauges. I will come to that, those instruments later on. Dial gauges, or we can measure, we can use the LVDTs for such type of measurement, or maybe use strain gauge rosettes for the measurement of such type of deformations, right? So you can see in this figure, the slot has been created, and you can see the slot, the direction is already defined, right? The direction of this plane is already defined, and we are trying to find out the stress in this direction, and the magnitude we are going to measure with the dial gauge, which is connected with the hydraulic jack, right? So, all the three parameters we are measuring by using this flat jack technique. Like in this figure, you will see flat jack has been inserted. Not only this technique is being used in for the rock, but you can see this civil construction. People are using it to measure how much is the stress which is being developed in a brick wall. Maybe multi-story building, we are interested to find out how much is the load coming on these walls. So we can use this flat jack, and you can see the plane is defined, dial is there, and we have the direction will be defined in this direction. Okay, so like in this figure, you will see flat jack, plane is defined. This is a D-shape flat jack. Then we have with this valve, you can put some oil so that it can inflate, and we will try to counter the stress which is developed in this wall to find out the pressure developed in the wall. So in actual rock conditions, you can see we can cut it by some cutters, and then we are fitting it inside for the method which has been discussed so far. Okay, So then there is a problem on this flat jack. We will discuss in maybe next class. It will be better to find out the stress tensor. No? I could not come to that point. Like at any point of time, at any point below the surface of the earth, we can define the stress at a point, and the stress is maybe the principal the stresses in a principal plane. Definitely we'll get the three values of principal plane stresses. But if I'm making out of principal plane, so and at that point we will get some shear stresses also. So we have to have a measurement of all these things. So we will discuss this thing in next class in more detail, and I will try to add some more photographs in the presentation itself, so that the problem we are facing with the blackboard, we can sort it out. And okay, so if any questions are there, you please come forward. Hello. If any questions are there, please come forward.
So I didn't quite understand that part where you said the stress change in excavation, and then when it's not excavated, like there's a change in stress or something.
Oh, you could not understand the change in stress.
Yes, so like the stress field, like the thing that you explained, like can you explain it again, maybe? Hello.
Yeah, so I was talking about when I'm making excavations. Na, a very simple example I used to give to the student regarding, I don't know whether, have you seen a mosquito net?
Yes, sir.
Mosquito net, yeah. So in a mosquito net, you will see that there are horizontal threads are there and vertical threads are there, right? Okay. Horizontal threads and vertical threads. Is it okay?
Yes, sir. Yes, sir.
Yeah. So if you can, so the density of these threads are there, na? So there is a fixed density of threads are there. So in the same way, we are assuming our things to be in the stress field. Horizontal threads, horizontal line representing the horizontal stress field, and vertical line is representing vertical horizontal stress field. Right? Right. Now,
Yes.
say for example, if I'm inserting any sort of object, maybe your pen, into that mosquito net, do not do that. So what will happen? It means that if I'm inserting any pen or anything into that net, it is going to create a small opening over there, and you will find that the threads are getting shrinked, and somewhere the number of threads will be more, and it is going to nicely follow the circumference of your pen. Okay, so this is also happening when we are making underground opening or surface opening into the rock mass. These stress fields are getting affected, and the stress fields are getting shrinked and concentrated at a particular points, and it will follow a point, and then again it will rejoin it. Okay, so similar way, so that's why the concept of in situ stress and the induced stress is coming. Okay, so am I clear?
Yes, sir.
Yeah, so so this is the reason. So this is the reason how in case of rock also the induced stress and in situ stress are being discussed. The same principle is being applied. Like if you can see the river water, right? The river water is flowing and there is a pillar of a bridge. So what will happen? Once the pillar starts, before that the water separates out, and then again it combine with each other and follow the stream, right? So the place where the pillar is standing, bridge of a pillar is standing, there is a separation is happening, and you will feel that a lot of eddies are getting formed over there, and the concentration of the water at the force which is being applied on the bridge pillars are very high on those points. Okay, so this is also the same concept is being there when I'm making excavations below the surface.
Thank you, sir.
Am I clear?
Yes, sir. Yes, sir.
Okay. Okay. I will share some photographs also. I will add some photographs, whatever I have drawn over here, and I will share with you so that you can have a more thought into that, and you can discuss little more and more interactive. Okay.